Okay, well, continuing on talking about acids and bases. So we're going to look at a couple different types of problems. Hopefully, watching me, you will learn some tools and some of the ways to attack these problems. So here, we get the equilibrium constant from the pH. We have a zero point 0.1 molar weak acid, and we find a solution has a pH of 4.25. What is the Ka for the acid? So you got to be careful about this because I am training you this way, but start thinking about what you're doing here. So HA, so you're probably thinking, okay, this is 0.1, this is 0, 0. We're going to shift right, and then 0.1 minus x, x, and x. Our Ka is going to be H plus A minus all over HA. You're like, what do I find? What do I look for H plus? So we're given the pH. So H plus is 10 to the minus pH, which in this case, you can just look it up. And 10 to the minus, so I should write this, 10 to the minus 4.25. So you can tell this, then your H plus is going to be 5.6 times 10 to the minus 5. And I'm going to go ahead, I'm going to store this variable. I can store this variable as x in my calculator. But if you want, you just put in the numbers, Ka, it's going to be 5.6 times 10 to the minus 5. I may be able to do, I'll just use this as the answer. And that's 5 squared all over 1 minus 5.6 times 10 to the minus 5. From the bottom was 0.1. 0.1. Actually, I may make that a little more explicit so it looks better. 0.1. So answer squared divided by 0.1 minus second answer. And we get 3 point, how many sig figs? This is 3.16 times 10 to the minus 8. So, by using pH, you can figure out the acid dissociation constants. So, if you know the concentration of the acid, you can figure that out. So, maybe you could look this up to see what the identity of the acid is. One thing you could check. So, sorry, I just had to sneeze real fast. Okay, so next example, we're going to get the percent ionization. So I like to think of this. I like to say that my wife and I, when we were in our honeymoon, we were like weak acids. So weak acids are like the clingiest couples you've ever met. So my wife and I did not spend every second together, but I mean, like, so for instance, we didn't go to the bathroom together and we showered alone. But other than that, we pretty much were together the whole time. And we are also frequently like that when we travel. Weak acids, they really stay molecular. They don't break apart very frequently. They're like the ultra clingy couple that you can't stand. And I will use this now to prove this to you. And so what is the percent ionization of a 2.5 molar nitrous acid solution? Ka is 4.6 times 10 to the minus 4. So let's figure that out. And the percent ionization is how much breaks off of the original amount times 100%. So we're going to see how much breaks apart, and we're going to divide it by the original, by the 2.5 molar, and then multiply it by 100%. So initially we have 2.5 molar of this, 0 this, 0 this. We shift right, plus x, so 2.5 minus x, x, and x. So our Ka equals this. So 4.6 times 10 to the minus 4 equals x squared over 2.5 minus x, which means x squared over 2.5 is approximately equal to that, or x equals the square root of 2.5 times 4.6 times 10 to the minus 4. And, oops, as I drop my iPad again, sorry. Oh, and it zoomed out. So 2.5 times 4.6 e minus 4, square root of that, and we get 0.0339. So that is how much breaks apart. So we have 0.0339 divided by 2.5, right? So we started off with 2.5 molar, and that's how much breaks apart. So divided by 2.5, and we get 1 point, how many sig figs? We have 2 sig figs. So this is, and this, well, I should say, times 100%. This is 1.4%. So that means if you're looking at a 2.5 molar nitrous acid solution, 98.6% of it is nitrous acid, and only 1.4 is broken apart. So it tends to really, really want to stay molecular, and that is why it's a weak electrolyte. It really doesn't want to break apart. Okay, so what about mixtures of acids? So what happens if you have a strong acid and a weak acid together? So in this case, and also water is a weak acid as well. It autoionizes. How do we deal with this? You deal with this with something called the common ion effect. So if we have, here we have a mixture of 0.1 molar hydrochloric acid and 0.1 molar formic acid. So we have to do the common ion effect, and hydrochloric acid is a strong acid, and what they have in common the common ion effect, and the common ion effect is the hydrogen ion. So you see here initially formic acid 0.1, hydronium or hydrogen ion 0.1, formate 0, so we shift right, and then we have the Ka equilibrium value, and we can this is a nice and easy problem because you notice this, you can discount this x, and then the 0.1 goes away, and your x equals just 1.8 times 10 to the minus 4, and then the hydrogen ion is just 0.1 plus that, and if you don't have enough sig figs, really, it's just 0.1, and you really can't tell that the difference. So here I've blown this up for you to show you it in a little more detail, what I just said, where you have the 0.1s there, and it's really the same thing as those up there, but if you wanted to see it with a little bit bigger writing. And okay, so let's talk about strong bases. We talked a bit about strong acids, and let's talk about strong bases. So our strong bases are lithium, sodium, potassium hydroxide. We could keep on going on, and I'm saying down here. So we could have lithium, sodium, potassium, rubidium, cesium hydroxide. Those are all strong bases. Maybe you see a pattern. Also, strontium, calcium, and barium. Maybe you can include magnesium. You can see here it's I don't necessarily agree with the book in here. I don't think calcium hydroxide is a strong base. Even strontium or barium hydroxide, I mean, so you can drink calcium hydroxide. It's called lime water, and it's not going to bother you. It's actually used as an antacid. Whereas if you drink sodium hydroxide, you're going to the hospital, and you better hope you don't die, kind of thing. So if you see here the strong acids, I've told you to memorize them there on the left there, hydrochloric, hydrobromic, hydrotic, nitric, sulfuric, the first hydrogen, and perchloric. The strong bases are even easier. They're just the first two columns of the periodic table. And one thing about the alkaline earths, the second column, not all of those are really strong bases, but magnesium hydroxide, the salts act like it's a strong base, which I'll cover that soon. So keep that in mind about the alkaline earths. I'm not including beryllium. Beryllium's just really toxic, and we tend not to use it for anything because it's just so toxic. But beryllium would also be included in that list, but it's so rare and toxic. So here are some common weak bases, and you might notice a couple things, that they have these terms, amine. So amine comes from so an amine is a organic molecule. It has so it's like ammonia, but it has an organic molecule attached to it, and those are known as amines. That well, not necessarily ammonia. It just has nitrogen in it. So you'll hear when you hear of nitrogen attached to an organic molecule, you'll hear the word amine. So and you'll start hearing it more and more without you notice it. So things like amino acids, or maybe amphetamine, and vitamin used to be vital amine. They're not all amines, but so you'll hear the words amine quite a bit, and so they're really just organic molecules that have nitrogen in them, and they tend to all be bases. And I mentioned the word alkaloid. Those are plant-based alkaline things. It's more than just that. I mean, more than just amines. Well, they are. A lot of them are amines, but the alkaloids, other amines, are weak bases. You can have other weak bases like carbonate and bicarbonate, for instance. Okay, so weak bases. So let's talk about strong bases. What is the hydroxide ion concentration and pH of each solution? So first one, A, 0.225 molar potassium hydroxide. That's easy. Potassium hydroxide is just plain old hydroxide, so the hydroxide ion is 0.225 molar. I like to do the POH way. I would do the POH is minus log of 0.225, and then do 14 minus the POH is equal to the pH for that one. And let me do this real fast. So minus log 0.225 and 14 minus answer. And this is 13, how many sig figs? 3. So this is 13.352. Same thing for the strontium hydroxide. Notice though, it's got a 2 there for the hydroxide, so the 0.0015 molar strontium hydroxide is 0.0030 molar. Same idea. POH is minus log of 0.003, so minus log 0.003, and this is equal to 2.52, and then 14 minus 2.52, 14 minus the answer, and we get 11.48. And I like to do it that way. You can do it the other way with the equilibrium expression, the AOH plus H plus is 10 to the minus 14, solve for the H plus that way, and do the minus log of that, but I like doing it the logarithmic way. So whichever way floats your boat. Okay, so now we're going to study how to find the hydroxide ion concentration and the pH of a weak base. So what is the hydroxide ion concentration and pH of 0.1 molar ammonia? So what I've written here, ammonia plus water makes ammonium plus hydroxide. This is considered chemistry common sense. So this is known as a hydrolysis reaction. This is a reaction of something with water. You should know that ammonia is a weak base, and that especially it says a weak base. It tells you it's a weak base, so you should know that a weak base is a proton acceptor, and solution is water, so it's going to accept a proton from water. So you should be able to logic your way through this. So then initially, we're going to have 0.1 0 and 0. Water's a liquid. It's not included in equilibrium. We're going to shift right. Shift right. Equilibrium is going to be 0.1 minus x, x, and x. Our Kb, this is going to be ammonium, excuse me, hydroxide, all over NH3. So 1.76 times 10 to the minus 5 equals x squared over 0.1 minus x. We can apply the x is small approximation there to get x squared over 0.1, which means, so x squared equals 1.76 times 10 to the minus 6, or x equals the square root of 1.76 times 10 to the minus 6, which I don't know. I can't just, this one I can't do in my head. It'll be something to the minus 3. This is 0.00133, and so this also equals our hydroxide ion concentration. So this is part 1, and the pH, so 14 minus the pOH is pH. So 14 plus the log of 0.00133. So pH is minus log, so minus a minus log is that. So 14 plus log of the answer. And this is how many 3 sig figs? This is equal to 11.123. There. So there you have it. And so recap for this one. pH, hydroxide ion concentration and pH of a 0.1 molar ammonia solution. So from the fact that, and you'll be given the Kb. So you should know ammonia is a base and it will react with water. It's a proton acceptor. Will form NH4 plus and OH minus. And then set up your ice chart, 0.1 initially ammonia, and then you should know you're going to shift right with, and then be able to get the extent of reactions there to get the equilibrium values. And then your Kb is your products over your reactant, discounting water because it's a liquid. Put in the variables. If you want to use your awesome calculator to solve for that, go ahead. If not, discount x and get x equals 0.00133, which is also the hydroxide ion concentration. And that's one of the things we were asked to find. And then use the hydroxide ion concentration to calculate the pH. Okay, so here, so just so you know, for acids and conjugate bases or bases and conjugate acids, if you take its acid and its conjugate base, you multiply together, or base and conjugate acid, those equal the Kw. So Ka times Kb for an acid conjugate acid base combo is going to, the combination of those is going to be Kw for water for at 25 degrees Celsius, 10 to the minus 14. And also, because of this, so some cations can be weak acids. So we just learned this up here in the ammonium direction, H4 plus, going the other way. It's an acid. It's a proton donor. So cations can be weak acids. So ammonium and then ethyl ammonium here. And you see some of these, they use these in cleaners. So the bleach wipes, they also use them to if you ever go to a meat shop, like a butcher, they'll spray these things on the cutting surfaces. So they use as disinfectants. Those cationic surfactants, as they're called. They're good antimicrobial properties. They're what they use in bleach wipes as well, and dryer sheets too. Dryer sheets and hair detanglers and conditioners have these in there. So you see these, and they are weak acids. Also in well, because the relationship Ka times Kb is Kw, the stronger the acid, the weaker the conjugate base, and the stronger the base, the weaker the conjugate acid. So, and some cations can also be weak acids. So aluminum, for instance, aluminum plus 3. Aluminum plus 3 is going to react with water. It's going to form a 6 water complex like this. And you can actually donate one of the protons, this aluminum with 6 H2O. This is known as a ligand. This complex, this H2O ligand, can be a weak acid. So certain salts that have cations in it will also act as weak acids. And we will talk more about salts and the acidity and basic nature of salts in the next lecture.